talk about part 4 of the lab, and then I also want to talk about, well, I was only able to do one problem. I want to do a problem on series parallel, and then I'll cover the other version in lecture today. Okay. I am assuming that you did parts 1 through 3 already, and if you have questions on parts 1 through 3, please hold off until I'm done with this discussion so I can answer your questions. Okay, because otherwise I'm going to be going all over the place in my lecture, my presentation. Okay. So in part 4, we're going to be looking at a device called a diode. And you can think of a diode as basically an element, a circuit element, that only lets current move in one direction. And the symbol for a diode in a schematic diagram looks like this. I did put a module, a link in one of the modules for this lab. It's a Khan Academy video on diodes. It really talks about the basics of how it works, but it doesn't really go into the applications. You can go online and look at the applications. So based on what happened this morning, I don't have a lot of time to go into the diode applications. So you can go online and search videos, and you can find there's tons of applications. This is a non-linear device, meaning that the voltage and the current are related to each other in a non-linear fashion. Okay. So what it does is it lets current go in this direction. So the diode, this triangle pointing with the peak here pointing to the right, saying that the current is going this way, and this means forward biased. It means that the voltage here is higher than the voltage. So the voltage on the left-hand side is greater than the voltage on the right-hand side. The actual potential here is higher than the potential here. And so the current goes from left to right, at least in terms of how I drew it. And so we say that that's a forward biased diode. If the right-hand side was higher than the left-hand side, then we would say it's reverse biased. Can you see that red? Does that red come out okay? Because it's an old marker. Looks okay?
Yeah, it looks okay.
Okay, all right. So when this side's higher in voltage than this side, then it's reverse, or high in potential than this side, then it's reverse biased. When it's reverse biased, ideally no current will go that way, but in reality a little bit of current leaks through, and you're going to measure it in the lab. Okay, you're going to measure it in the lab. All right. Typically, when this turns on, the voltage across it, and this depends on the type of diode you have, varies from between 0.2 to 0.6 volts. And maybe it could be as high as 0.8 volts. The diode can be made out of different materials, such as a silicon or germanium. And so this number where it turns on just varies. Okay, typically it's around 0.6 volts in that ballpark. Okay. All right, questions so far? Okay. So you're going to use this to look at the IV curve. So if you actually plotted current here, voltage across the diode here, your graph will kind of look like this. And this pretty much stays horizontal, pretty much, up to a point where you put too much voltage in the backward direction, so it actually breaks down. You essentially ruin it. And then it'll conduct, and then it'll actually go like that. Okay. you'll exceed the breakdown voltage. Now diodes, most diodes are designed so that you don't go to that breakdown voltage, okay? You actually don't want to get to this point because you'll mess it up. But there's some diodes called Zener diodes where you can actually, they're designed so that when you reach this point, you want it to work. So there are Zener diodes where you have to, this thing will still work when you reach the breakdown voltage, okay? The most diodes, you do not want to go past this point where it breaks down. Otherwise, it's useless. Okay. So the Zener diodes are designed to exceed the breakdown voltage. Okay. These, like I said, are nonlinear devices. Capacitors, resistors, and we'll talk about inductors later. Those are linear devices, where a voltage and the current are proportional to each other. Okay. Now wait, you might say, well, what about the current through a capacitor? Well, when we talk about AC circuits, you'll see what I mean by that. Okay. You won't see that here when we talk about capacitors and DC circuits, but when we talk about capacitors and AC circuits, you'll see that the voltage and current are proportional to each other. But this is basically one of the first, other than the light bulb, nonlinear devices that you would study in circuits. And it has a lot of applications. You can take the voltage from AC, from your AC socket, for example, and rectify it so you can take out the negative part of the signal. Okay. Which is called a half-wave rectifier. You can also use it as for a full-wave rectifier, and you might have heard those terms before. So diodes are used for that. So basically, you're trying to get rid of the AC component of your signal and make it all DC. So diodes can be used for that. Diodes are used in computers. Combinations of diodes are used to make transistors. Okay, I'm not going to go into the physics of how they work, because that would require me to go into semiconductor physics. I don't want to do that. Okay, so we're not going to talk about how they work, the physics behind them, but we just want to see what they can do for us. That's all. Okay, and really for this lab, it's just an example to show you a nonlinear relationship between I and V. And then the other thing is you're going to learn how to wire the circuit. Okay, because this is a little bit more complicated than you've encountered before. This is probably the most complicated circuit you will do in this course. Okay, obviously real circuits are much more complicated than that, but at least it gives you an idea of what you're going to be encountering. This is really I think the most difficult circuit in this course you'll deal with. If you can wire this, then the rest of the circuits we cover this semester should be pretty easy to wire. Okay. All right, so when you consider wiring the circuit, because right now it looks complicated, you're going to do the following. You're going to be, you want to ignore this part. When you're wiring it, you want to ignore this part. Okay? So you do this. You take your power supply, which is going to be at 12 volts, right? So yeah, that little plug thing, you're going to set it to 12 volts. You're going to connect it to a resistor. The purpose of the resistor is to limit the current through your circuit so you don't burn the diode. Because if you put enough current through the diode, you'll burn it. Then you'll have another resistor. And I need to talk about the other resistor. So I would wire this first. So wire this first, because it'll make it a lot easier. Because if you look at this whole thing, you're going to get confused. Wire this first. But let me talk about this thing right here. Okay, that's called a potentiometer. It's basically a variable resistor. So let me go to my camera here. So now I'm going to start switching cameras on you guys. Okay. Let me leave it there for a second. Oops, I mean, Let me leave it there for a second. I'm going to unplug my microphone so the sound won't be as good, but I don't have enough USB plugs. Okay, so the device you're going to be connecting, although I'm using a different slightly different version of it, is this. This is a potentiometer. Notice there are 3 wires coming off of it. Okay, and there's a dial. The dial is used to vary the resistance. So what in the world is this thing? Well, let me go back on the board. Okay, let's go back to the board. Basically, you can think of a resistor as a long wire. These are the ends of the wire. If you take a multimeter and you measure the resistance between these 2 points, you'll get the full resistance of your resistor. Well, what if I attach a wire here like that, and I fix it in place? How many resistors do I have now? Well, I have this resistor and I have this resistor. This resistance plus this resistance has to be equal to the total resistance of the wire. Okay. If I solder a wire here, and I measure the resistance between these 2 points and these 2 points, it's got to be the same as this. Well, what if I set it up so that I can put a wire here and just slide it up and down? That means I can vary this resistance and I can vary this resistance, but I can keep this constant. And that's what the potentiometer is. That third terminal is essentially this guy moving up or down. You can call it the wiper or the slider, whatever you want to call it. Those are the names, right? This is called the wiper or the slider. Okay. So when you hook, first of all, when you hook this up, you use the 2 end terminals. Let me go back to the camera. So when you originally hook up the circuit on the board, when you look at this thing, you use that terminal and that terminal, the 2 on the end. Okay? You use the 2 on the end. So you use these 2 to make this, to wire this up. Let me draw that. This is 1,000 ohms, so you basically get the full 1,000 ohms. You have 1,000 ohms plus 560 equals 1560 for your circuit, okay? So you wire it up like that. So you use the ends of the potentiometer. Then you take the middle one, okay, you take the middle one and you connect it to one end of the ammeter. Then you take the other end of the ammeter and then you go to the diode. And then you take the other end of the diode and you go to your ground. Granted, you can have a ground in the circuit, you call it the neutral. And then you connect the voltmeter across the diode. Okay, so you wire this part first, and then you wire this second. That'll be less confusing for you. Does that make sense? Almost. I think, Jacob, when you actually go and actually do the physical wiring, it'll be a little bit easier than me talking about it up here. But I think if you try to wire it as you watch what I just said, it should be straightforward. Okay. It looks hard at first, but it's not that bad. Yeah, you're gonna have to use 2 different meters. So what you mean? What do you mean the second part? Is this part?
Yeah.
Middle terminal on the potentiometer to ammeter. The other side of the ammeter to diode. The other side of the diode to ground. And again, remember, you have the ability to replay this when you watch the video, so you can go over it over and over again. That'll help you. Okay. So you go from the middle of the potentiometer to the ammeter, the other side of the ammeter to the diode, the other side of the diode to ground. Okay. Yeah, that's a good question. Well, first of all, typically diodes look like this. They're different colors. They have a black line here, and basically this is closer to what we call the cathode, the negative side. So this mark is closer to the cathode. So I'm going to show you the entire circuit built that I built on the I keep saying printed circuit board, but on the proto board. So let me switch cameras. This is the circuit I wired up. Now your potentiometer is different, is actually nicer than this one, because your potentiometer fits into the board. This is the potentiometer, so you can actually fit it directly into the board. Okay, so Tyler found one that goes directly into the board. It doesn't matter which way you put it. If you can flip this over too if you want, but it was easier for me to hook things up this way. Okay. In your particular case, the diode has like an orange color to it. So this is the diode. It's tiny. I mean, compared to my index finger. The body of the diode is tiny. Look at that. Do you see the black line on it? Can you see the black line on the diode? Yes, no? Okay, so it's right there. So this is what the diode looks like. They're different types, okay? Some of them have a completely black body with a gray line on it. Okay. But this particular one is kind of an orange colored. And there's some silicon in there that acts as a diode. It's really tiny. Okay, so you should have probably two of these in your kit. So my power to the circuit is down there. So I'm showing you this so you can watch the video over and over again. Okay. Your power to the circuit is right here. So I'm going to bend it further down. And I told you guys last week I just taped it so that way I don't have any problems. Okay. Well, let's take a look at this circuit. There's my 560 ohm resistor. It should be, trying to remember the colors, green, blue, brown. Although it's actually kind of hard to see the colors on it. Actually, maybe on this camera you can. Because I have it, because it's zoomed in so much. It should be green, blue. It is green, blue, brown. Okay. And then I have this jumper wire that goes to the, oops, sorry, hold on a second. That goes to the potentiometer. This is the other side of the potentiometer that goes to ground. And then I have the diode that goes to the middle connect. It's hard to see, but it goes to the middle part of the potentiometer. And you notice that you don't see a physical connection here. There's a wire right here. Guess where the wire is going to go? Guess what's going to go between this wire and that end of the diode?
is it the ammeter, so it's in series?
Yeah, so I'm going to connect the ammeter between these 2 points. Okay, and that will complete my circuit. So that's the only thing missing from my circuit. So I'm essentially ready. All I got to do is connect the ammeter. I can use alligator clips, one here and one there, and I'm set.
Where is it connected to your voltmeter?
So you have to hook it up across the diode, right? So all you got to do is connect the voltmeter across this terminal and that terminal. Oh, that's too far up, so hold on a second. Let me tilt the camera. So you're hooking it up across this, right?
Oh, okay, so you're just holding it to it, essentially, whenever you're going to measure?
Yeah.
Okay.
Yeah, which can be problematic, I guess, because you don't have enough alligator clips, right?
Yeah, no, I only have one set.
Okay. Yeah, that makes me think we should probably give you guys more alligator clips. Okay.
So I saw that your battery supply is taped, but what's the little green part that has the wires coming out?
Right, that's in your kit, right?
I was trying to find it, so that's not with the batteries, that's somewhere else?
Yeah, you have a blue box. I mean, you have a box that's white and blue that has... that contains this, right? It's too close. Right. Your plug, this thing, came in a white and blue box, right?
Yeah.
Okay, so in there should be several adapters. One of them is this one.
Oh, okay, awesome. Thank you.
Okay, and then you can connect the wires to them. That's why you want to use that one. You can just put the wires in there. They just stick in there. Hold on a second. They just stick inside here. So there's several adapters that come in there, and you want to use this one, the green one, the one with the green end. Take a look at the video that Tyler made. Okay? You want to take a look at the video that Tyler made because he goes through this.
Did you email that video to us?
Yes, I emailed it like last week, or I think.
Perfect.
And unfortunately, I think I emailed several videos last week. I can't remember how many I sent. Sorry. I think I sent 3 videos. I can't remember exactly. But included in that is the Ohm's Law video. But they were like in 3 separate emails. So you can use, and you can watch this video to see how yours, you can hook up yours. You don't have to hook it up this way. There's a million ways you can hook it up, but you kind of already probably know how the holes are connected on your proto board based on what you see here. Okay. Any other questions about the wiring? You have a question, Jacob? Well, in my circuit, you connect one here. You see the wire that's real close to you? And the other one right there. Just use alligator clips. Now you're putting it in series. You always put the ammeter in series. So same as the, what I set up on the board. You go from the middle potentiometer of the potentiometer to the ammeter, to the other side of the ammeter to the diode. That's in series. Okay. Now the question is, what you set the ammeter to. What setting do you set the ammeter to? And it's kind of important that you do it properly. So when you initially set the circuit up, before you collect data, you need to play around with the circuit. You need to play around with the potentiometer so that you know what the maximum current is in your circuit. Okay? You have to adjust the dial on the potentiometer so that you know what the maximum current is. The maximum current is probably going to be around 20 milliamps or less. Most likely you want to be at a 20 milliamp scale, but you want to check me on that. Okay, so I would put this on a 200 milliamp scale and rotate the dial on the potentiometer just to see that I'm correct. Okay, and if your maximum current is below 20 milliamps, then okay, go ahead and use a 20 milliamp scale. Okay. So you do have to play around with the circuit first before you collect data, but always start with a higher current setting and then move down. All right. Your goal is to graph this, and you need to collect about 26 data points. You need to collect a bunch of them. And you might say, well, why do I have to collect so many data points? And here's the reason. And the theoretical relationship between current through the diode and the voltage across the diode is given by this expression. Okay. Notice that it's exponential. So exponential growth means that the current increases rapidly. So you're only going to graph the data from table 3. I'll repeat that. You are only going to graph the data from table 3. Don't graph the data from table 4. And I'll tell you why in a minute. Okay. So your data is probably going to look more like very difficult to draw when your graph is going to kind of look like that. And this thing gets really steep at a point. In order for you to get enough data so you get a good curve fit, you actually have to get enough data points over the most curved part of your graph. That's why you need to take 26 data points. You want to get enough data around this point where it's really curved so that you can get a good curve fit. The number of data points up here doesn't matter. It's pretty much straight up. This part of the graph, if you blow this up, it's really curved. But this part of the graph is where you want to collect most of your data. And because it's exponential, the current increases very rapidly when it turns on. What do I mean by very rapidly? We're talking about you changing the voltage across the diode by 0.02 volts and the current doubled. That's how small. I mean, that's how steep it is. It'll be very rapid to change. Okay. Now, on the potentiometer, this thing is not an expensive potentiometer. It's a cheap one. So when you turn this over one full turn, you go from 0 ohms to 1,000 ohms in one turn. That's not very sensitive. You can buy a good one where 10 turns gives you 1 kilo ohm. As a result, if you want to vary the voltage very slightly, I mean, you can't do a quarter turn. If you do a quarter turn, you're in trouble. I mean, if you do a quarter turn on here, you go from here to here. Okay? You don't want that. I mean, you just got to just touch the dial, just barely, so that the voltage just barely increases, and then measure the current. And then do it again. Just touch the dial so that the voltage barely changes across this thing, and then measure the current. Like I said, you can get a 0.02 increase in voltage drop across this thing, and the current will double. That's how fast this rises. This is why I'm telling you, you better play around with the circuit, get a feeling for how the current varies with this dial before you collect data. Otherwise, you're gonna have to start over. And you don't want to have to start over if you have to collect 26 data points. Does that make sense? I hope so. Okay. So then you have to do a curve fit to this. All right. You're going to fit to this equation. So let me just say a couple about this equation. I sub S is called saturation current. Sorry, I have to write up here. And it's essentially, when you run it backwards, this is almost a straight line. So that's basically this current. It's pretty much that current. Okay. Asymptotically. When you go in this direction, this V is negative. When it's reverse bias, V is negative, and as this gets bigger, as V gets bigger, this term gets really tiny. And this term dominates. Okay. All right. V sub T is Boltzmann's constant times the temperature over E. So K, and I write it funny like this, is 1.38 times 10 to the minus 23rd joules per Kelvin. If you have physics 215, you've seen Boltzmann's constant before. E is the magnitude of the charge on the electron. Basically, this is a conversion from joules to electron volts. Okay, that's really what it is. You can just say this is the number of joules per electron volts also. Because this is in joules, that's in electron volts. And you get volts out of it. Okay, and then T, the temperature in Kelvin. You need to know the temperature in your room. How are you going to find the temperature in your room? Anybody want to? Yeah. So how do you do it? Anybody want to venture to? Just be creative. How would you find the temperature in your room?
The thermostat?
Good, the thermostat. You have a thermostat, and you're right. Just look at what the thermostat reads. If you don't have a thermometer, use a thermostat. Use what you got. Okay. And so you take your, but you got to take the thermostat reading and convert to Celsius, though, right? Yeah, I'm assuming you guys know how to convert from Celsius from Fahrenheit to Celsius. And then you got to add 273. So this T is the temperature on the absolute scale. So you take 273 plus the temperature in Celsius. That's this term. This number is approximately 0.025 or 0.026 in that ballpark when you're at around room temperature. This N, ideally this N is 1, but it's not 1 for all diodes. Okay? This is basically a fudge factor when you do the theory on these things. So this is, a lot of times this is a number between 1 and 2, although the diode I used over this last summer, N was 1. So this, I mean, it was 1, and then the insertion was at a 6 decimal place. Okay. The yours might not be 1 because they're using a different diode than what I used when I collected data. Okay. So the things you got to think about is, 1, make sure you collect a lot of data points here where it's curves. Turn that dial slowly. Okay? And your goal is to figure out this term and this term from your curve fit. Really what you want to see is, does your data fit the theoretical curve? It should fit well. So let me show you my data that I collected over the summer. And I ought to warn you, I've had trouble this morning running Davis with the camera software. So just give me a second here. By the way, I'm going to plug in my microphone so you can hear me better. All right, so let's do this. All right, so this is my diode data. Yeah, I'm sorry, I missed those questions. Yeah, the top V in the equation, hold on a second. This V is this variable. This I is this variable. So yeah, this is your X, this is essentially your X coordinate. Okay, let me go back. So this is my data, and it's really hard to make things larger. Part of it is because I'm using too many resources on my computer. Let's try something. Oh, that's the wrong one, sorry. Okay, so that was the curve fit I got over the summer. Okay. And my I sub S, if you can see it, was sub picoamp. It was about 0.4 picoamps. Of course, the uncertainty was 100%, but that's okay. That's how it's going to be. And then my N, can you guys see the N value is about 1 and the uncertainty is at a 6 decimal place. In fact, what I did is I copied this into the lab, so I can show you the graph later. The one thing I need to do is talk about how to do the curve fit, because Davis does not have that curve fit equation. And if you're using graphical analysis, it does not have that curve fit equation. Okay, so let me go back to the camera, to the board. This equation does not exist in Davis or graphical analysis. So you actually have to define a curve fit. So in graphical analysis, and I can't show you graphical analysis because it doesn't work on my computer. Okay, the old version doesn't work on my computer. But if you go in graphical analysis and when you do the curve fit, if you type define fit, and then you type in the equation, then you can do the curve fit. You would type it like, you would type it like this. Whatever that number is, I'll just put a number. Probably want to use parentheses. I mean, you can type it like this, or actually you probably make this an X. By the way, when you do it in graphical analysis or side Davis, it's pretty much the same thing. So let me show you the side Davis curve fit that I typed up. Let's see. So you go to analysis and you're going to hit fit. Oops, sorry. Okay. So you go to analysis and you hit fit wizard. Okay, so it's not showing up on your, give me a second. So you click fit wizard and then you want to choose user defined. And then you can create your own curve fit. Okay, so you can tell I've created quite a few of them. My fifth one is essentially what I use for the lab. Okay, so I can choose this one. Or if I want to, I can type one in. A star. I can't type. That's my curve fit equation. I can make this a B. I'll make it a capital B just to make it different. So my parameters A and B. So I typed in my equation. It might be, let me just change it. I'll just change it to 0.025 for now. Okay, and then I'll save it. And I'll do a fit. Click on this. And they'll tell me what range. I'm gonna go from 0 to 0.796. So I want to go over the entire range. I can change the tolerance. If I want to. And I hit fit. Uh-oh. Missing parentheses. Was not happy. I messed up. I typed it in wrong. And it's very unhappy. Sorry, it screwed up. Okay, let me restart this because it's not happy at all. Okay, let me try it again. I'm going to use the one I already had. Hold on a second. Okay, let me do the fit wizard again. And instead of me typing one in and screwing up, I'm gonna pick the one that I already had typed in. Okay, because I don't want to screw up again. I made a mistake with all the parentheses. And I'm going to fit over the entire range. So I just changed it, increase the tolerance. Let me do a fit and close. And so the fitting parameters, which you cannot see, there's another window that shows up, and for some reason you can't see it. So what I'm going to do is I'm going to do a screen capture. Actually, that doesn't help either. Hold on a second. Let me try to do a screen capture. So you can see that the other window that shows up. Hold on, I gotta do it one more time. Let me try one more time. Sorry for the delay. For some reason it's not doing it right. Anyway, let me show you what the window looks like. There it is. So you get a window that looks like that, and that window shows you the curve fit parameters. Okay, I'm not sure why my results are different this time. I think it's because it's tough to do the curve fit. So it shows me my A value and my B value. And then what I would do, okay, let me switch views again. Sorry, I'm switching things all the time on you guys. I would go to my graph. Oh, for some reason this graph looks terrible. I don't know what happened. That's very strange. I'm not sure what happened to my graph. It's just, the fit's terrible. I might have to retry. I would have to retry it later. But anyway, Okay, so I would go my graph, and then I can type in my curve fitting parameters. Hold on a second. Every time a new window pops up, I gotta keep switching. I can type in my curve fitting parameters in here. Okay, so how do I get that window? How do I create that window? Well, let me show you how you create the window. You create the window by going to graph. Oh, it doesn't even show that on the screen. There's at the top of the menu. There's a thing that says graph. Hold on a second. And then you hit add text, which it doesn't show you. I'm not sure why I can't show you this. But at the top of the window, this window, there's a thing that says graph, and just hit add text on the same layer. Okay, add text to the same layer. And then you can add this, you can create this text box. Okay? And then you'll have everything you need for your curve fit. Any questions? No questions, concerns? Are we okay on this? Okay, so let me mention a few things about the lab. And I have to be careful because I have so many windows open.
Question real quick.
Go ahead.
This is in the chat.
Oh, go ahead, Jacob, while I switch windows. Can we wait till the end, Jacob, and then I can take a look at your circuit? Can we wait till the end of the class? Okay. Then I can take a look at the circuit. It's not always easy to do this online. Okay. I'll say that. Sometimes it's hard to see things when it's online. So here is the lab. And I didn't have time to do this with the other group. My computer is responding very slowly, so I apologize. There's questions you want to answer here, so make sure you answer them, okay? That thing I highlighted, what does that mean?
You want us to write our own title?
Yes, okay. I think Harris did this. Notice the units on here, okay? Be careful with the units. Pay attention to units. Okay, so you're just going to enter values. I mean, you all had a Viva, so same thing. You're going to enter the values here. You're going to enter values here. Again, title. Watch the units again. Pay attention to the units. Really, you know, I'm looking for you paying attention to details and following instructions, the main thing in this particular lab. So, part 4, again, title. Enter all the data. And then table 4, so I didn't mention what you're going to do in table 4. So give me a second here. Let me talk about that part. For the table 4, what you're going to do, and Tyler does it differently in the video. What Tyler does is reverse the leads on the power supply, but really, all you got to do is flip this around. Basically, you're trying to see how much current leaks through the diode. And all you're doing is collecting the data. You don't plot it. Don't add it to this plot. Okay, because you're going to need to use a the 200 microamp scale to be able to actually measure anything. Okay, you can't switch scales in the lab because the resistance of the ammeter changes. When you go to the microamp scale, this resistance is the same size as this value. And that's mixed, that changes everything. Okay, when the current is in milliamps, if you change scales, well, you might blow the meter, but you're going to get a shift in your graph. So don't change scales. And so don't graph the material from table 4, because you got to use the microamp scale. Is that clear? Do not graph the stuff in table 4, because you got to switch scales. These multimeters are a little bit different. Okay, so let me go back. Notice that it says, why am I asking you this repeatedly? That wasn't from me, so. Record the room temperature as best you can. And then you're just going to answer some questions in the lab. There's not a lot to it. Okay. When it says show your work, show your work. The conclusions that it asks for you to do. You know, what did you find out in parts 3 and part 4? Okay, this is not going to be a formal conclusion. Okay, normally when I ask for a lab with a conclusion, it's not going to be it's going to be formal. These ones are basically, what did you learn in those sections? What did you find out? How does the voltage vary with current? Does it agree with theory? Okay. Basically, I'm looking to see if you don't answer it, then I take off points. If you answer it and it's okay, it's fine, you know. Or if you answer it and you say something ridiculous, maybe I'll take off a little bit. But I'm looking for you to think. You're thinking. I'm just trying to see if you're thinking. Okay. It doesn't have to be absolutely correct. You'll still get full credit on those conclusions. And don't forget, every graph requires a figure caption. Okay, so what I want to do is an example, unless you guys have questions on the write-up or anything. And you know, like I said last week, I'm assuming that you have collected the data from the first 3 parts of the lab. Oh, before I go on, somebody brought up a question, and I should tell you guys about it. How do we know the uncertainty of the resistance? When you take the multimeter, how do we know what the uncertainty of the resistance is?
Is it based off the multimeter scale?
Yeah, well, we're going to be a little bit more precise than that, because you have a manual that comes with the multimeter, and the manual tells you, it actually tells you the accuracy. It actually gives you an estimate of the random errors plus the systematic errors. So the multimeter will say, like, the resistance measurements are to 0.4% plus half digit. Okay? So that means if your multimeter read this, okay, plus a half digit. I'll tell you what the half digit is. Then you should quote a value like this. That's what that means. Now, what does a half digit mean? It's the digit after this. Half a digit means this next digit is a 5. But what do we say all the time? You keep only one sig fig here, so you round this to the even, and you leave it like that. Are we okay with that?
So would that be the same thing for on the color chart whenever it says the percentage uncertainty?
Yeah, in the color chart, it's a much higher uncertainty. In the color chart, yeah, it'll say like, I think it's, if the last band is gold. So on the color chart, it'll be like this. So then you would write something like this. Okay, this is from the color band, or you can write it this way too. Why did I write it like that? Why did I not use this format? Why is it that I didn't write 1,000? Right.
Because you need it to match the uncertainty.
Yeah, but also the zeros are ambiguous, right? When I write the numbers like this.
Yeah.
Yeah, so it's better to write it something like this, either this way. Oh, I screwed that up. Either this way or that way. Okay. But don't do this. I mean, I guess you can, but it's actually better to write it like this. Okay, because these zeros tend to be ambiguous. Although if you do write the uncertainty, that tells you at least you know that value to 50. But it's actually better to write it either this way or this way. So I just wanted to mention that. Okay, I just wanted to mention it. So I want to do an example on series parallel. And then I'll end it here. And then I'll answer the question. What if it's plus 5? I'm sorry, what do you mean plus 5? You're talking about what it says in the manual? Yeah, that's the half digit I was talking about, right? So that's the next digit. So basically, it would be this. Oops. Yeah, it would be this value. And it basically means half a digit. And remember that we said that we always keep one sig fig in the uncertainty, so you got to round this off to the even. You write it like that.
So then it's always going to be 0.4%.
Well, if that's what the manual says.
Okay.
Right, you've got to go by what the manual says, right? So if the manual said this, plus half a digit, then what do I do with this?
You round it.
Round to the even.
Yeah, you write it like this. There are certain exceptions when you can write two digits here, but I'm staying away from that because it just becomes confusing. All right. So I just want to do one example. And then we'll do a different version of it when we get to class. Okay, so hopefully the screen doesn't get blurry because I have so many windows open right now, so many programs open right now, so we'll see. I had a meeting one day where my computer said you're out of memory, and I had to reboot the computer in the middle of a Zoom meeting. So hopefully I don't get to that point. Okay. So I'll do the other version of this problem in class today. I want to just get you guys started. So I have this circuit with 4 resistors in it. R sub A, R sub B, R sub C, and R sub D. And I connect an ammeter between these 2 points. Okay, that's not a very good diagram, but I connect an, can you see the ammeter or is it too light? Is that okay? Okay. So I want to know the conditions, the required conditions so that I ammeter equals 0. So what condition must be satisfied so that when I put an ammeter between these 2 points, nothing goes through here? Okay? In general, something will go through here, and it'll go either to the left or to the right, depending on what RA and RB are. Okay? So what are the conditions? So first of all, if the condition is satisfied, what does that mean? Let's ask that question. If the condition is satisfied, what does that mean? Well, if the condition is satisfied, if I ammeter equals 0 and ammeter is ideal. What does that mean, the ammeter is ideal? It means our ammeter is 0. If that's the case, what does that mean? It means V at 1 equals then V at 1 equals V at 2. Furthermore, if current comes in here and then splits up at this node, the current's going to do this. And then the current's going to do this. Which means the current through here and the current through here are the same. Which means that I sub A equals I sub C and I sub B equals I sub D. Because the electrons are going here in one path. The electrons are only taking one path here. They're not going this way. Electrons are going this way. So whatever current is here is equal to the current here. Same thing for these two. As the current goes through this way, since nothing goes through the ammeter, it's all got to go through R sub B. So this has to be true. Okay, so now what? What else does that mean? Well, if these two are at the same potential, then the difference between this point and this point is the same as the difference between this point and this point. Which means then that delta V sub RA has to be equal to delta V sub RB. Furthermore, these two have to be equal. Well, I can use Ohm's law to write this. And I can use Ohm's law to write this. But we said that these two are equal, so I'm going to replace the C with an A. And we said that these two are equal. Now divide the equations. If I divide the equations, I get this. So if the current is 0 through here, this relationship has to be satisfied between the resistors. This is called the Wheatstone bridge. And it has been used for many years to measure the resistance of some unknown material. So what you can do is make these two known resistors, make this a variable resistor. You change R sub B until no current goes through here. So then you measure this, you measure this, you measure this, you know their values, and you can calculate R sub D. And you really don't use an ammeter for this. You use a device called a galvanometer, which is a device that measures current. And it uses the idea that if you run a current through a wire in a magnetic field, that wire is going to experience a force. So it's like a current detector. And so the resistance is much lower than that of a meter. Now another way to do this, to make the measurement, you can actually use a voltmeter, because the voltmeters nowadays have such a high resistance that there's no current that's going to go through here. And so you could just measure the potential difference between these 2 points. Once it reaches 0, your bridge is balanced. A balanced bridge means that there's no current going through here. All the current goes this way and this way. So you can use the Wheatstone bridge to measure resistance that are in the milliohm range. Okay. Any questions on this problem? So what I'm going to do in class is I'm going to do the general case when there is current going through here. How do we calculate? How much current is going through here? That's what I'll do in class. That's the first problem I'll do in class today. Okay, I'm going to look at the case when current's going through here. What do we observe? Questions? Concerns? Everybody okay? Got one more week before spring break. The next lab is based on the circuits I'm talking about in this example. The circuits I'm talking about in this slide are basically your next lab. Okay? That's why I'm going through this here, because this will be your next lab. Okay, so if you don't have any questions, I'm going to end it here, and I will see you at 2 o'clock. Oh, your circuit. Yeah, go ahead, Jacob. For the rest of you guys are free to go. Jacob, go ahead and show me your circuit. This is part 3, part 4. I'm going to unpin myself, because otherwise, and you can share your screen.